Okay, hello everyone. I will be presenting FPT, a fixed-point accelerator for Torus fully homomorphic encryption. So I'm the last talk in a session on homomorphic encryption, so I think I can be short about the motivation of this problem. What we're currently seeing is this data privacy paradox where more data is better, but data is being increasingly protected and regulated and subject to privacy concerns. This can be due to some privacy regulations such as GDPR, for example, and in general, those limit the availability of data. So computing on encrypted data is this new technology that allows you to solve some of these issues. Fully homomorphic encryption in particular is illustrated on the slide here, where a client can encrypt their data, the server processes the data in encrypted form and sends the result back. This allows you to extract the value from the data while still keeping it entirely confidential, and it has applications in financial, medical, and many other domains. On the slide here is shown a small example taken from the IDESH competition of last year, where there were clients sitting on sensitive genotype data, and the challenge was to compute a machine learning model on the encrypted data in this form. So this talk is about a hardware accelerator for fully homomorphic encryption. Why do we need hardware acceleration for this problem? Well, computing on encrypted data is still very expensive. This slide sort of tries to illustrate the problem. Firstly, doing computation in encrypted form can be up to a factor 1 million slower than doing the unencrypted computation. So we're really paying a performance cost of up to 1 million for this additional security guarantees we get there. This sort of translates to also a similar increase in energy consumption for these computations. Looking at the Torus fully homomorphic encryption scheme in particular, a typical application profile is shown on the right. And we see that this increase in computation cost is mostly attributed to two functions only. And those are the bootstrapping function and the key switching function. So whenever we do computations in TFHE, in Torus fully homomorphic encryption, really the majority of the computation time is taken by bootstrapping and key switching. So what we designed is a hardware accelerator that specifically focuses on the most costly of the two, the bootstrapping operation. Our hardware accelerator is shown on the slide here in the right. It is a quite involved architecture, and I don't have time in this short talk to cover all of the details, but I want to give you three key takeaways of this architecture. They're shown here on the slides. They are that we use a streaming architecture, batched computation, and a fixed point design. And I will shortly talk about each of these three aspects in more detail to give you these three key takeaways of our architecture. So firstly, we use a streaming architecture. What does this mean? Well, you can compare it to a factory processing belt. Data will move along the belt just like it moves inside our architecture. And as a result of this data movement, computation happens. So this is really how our architecture works. Data moves from the left to the right. It flows through the architecture, and computation is happening as a result of it. The benefits of this is that it involves low control overhead. We don't need to send the data back and forth, retrieve it from different places, send it around. And at the same time, it achieves a very high throughput because, we really just pump the data through without really being bottlenecked by constantly moving the data back and forth. The overall result of this is that we also achieve a very high utilization of our architecture, which in fact is very, very close to 100% total. This can be very different from a classical architecture where you have compute units that talk to a central memory, where typically it is much, much more involved to achieve high utilization of your arithmetic units. A second key takeaway of our architecture is that we solved the memory bottleneck for TFHE. So the classic state-of-the-art fully homomorphic encryption hardware accelerators, they are typically memory-bound. They are memory-bound because they operate on very large keys. These bootstrapping keys, these key-switching keys, they can be very large, from several megabytes up to gigabytes, and typically loading them from off-chip memory is the bottleneck in the computation. We solved this in our architecture by working on batches of inputs. So what we do is we group a number of inputs together. We call this a batch. And within the batch, we make a reuse of the same key. So we always use the same key for each element in the batch. And as a result, we can be entirely compute bound because we only need to load this key once to process the entire batch instead of doing it for each input separately. So really this maximal reuse of the keys allows us to be compute bound rather than memory bound. And typically it's very favorable to be compute bound because you can throw extra area, extra compute resources at the problem, whereas memory bound you're typically very limited by what is available in the current technologies. The last key takeaway is that we use fixed point representations in our architecture. And why do we do this? Well, the observation we made is that fully homomorphic encryption is inherently noisy. There is noise in the ciphertext and there is noise in the calculations. So what we do is we also use smaller intermediate presentations in our architecture while we do these computations. What this allows us to do is achieve higher efficiency because we're working with smaller numbers, and we still achieve identical accuracy. How do we achieve identical accuracy? Well, that's because we do not exceed the noise that is inherently in FHE. We use smaller values, we add some noise, but this noise stays smaller than the one that is inherently in fully homomorphic encryption. So we did this experiment shown on the right here, where we looked for the optimal representation of the values, and we found that really an up to 80% area reduction is possible. If you do the naive implementation, where you're on the far right of this graph and you implement everything with 53 bits of precision, which corresponds to floating point numbers, you have a very high area utilization. And what we did is really reduce this value. We work with smaller numbers so that we can use significantly less area in our architecture. So those are really the three key takeaways of our architecture in a nutshell. We use the fixed point representation. We have the batching of the inputs to reduce the memory bottleneck. And then finally, the streaming architecture, which allows us to achieve very high throughput. We evaluated our architecture in two ways. I would invite you not to look at all the details in this table, which is quite dense. You can look at those later. But the main conclusion here, where we compare against one concurrent FPGA architecture, also CPU, ASIC, and GPU implementations, is that FPT is currently the fastest bootstrapping architecture for TFHE. We are up to 3 orders of magnitude faster than CPU-based implementations. We are 2.5 times faster than in prior ASIC implementation. So this is really a custom chip, whereas we are programmable hardware, FPGA architectures, and the same holds for GPU. So the numbers you should really be comparing here is what is our main focus, is the throughput of our architecture. And yeah, so for example, compared to CPU here, we are almost 3 orders of magnitude faster. Now, one thing you could be thinking is, of course, throwing dedicated hardware at the problem, you will typically always be faster. You really throw extra compute resources. Also, the CPU, the ASIC, the FPGA are sometimes difficult to compare one-to-one. So we did a second experiment where we evaluated TFHE bootstrapping on AWS. So this is on the Amazon cloud. What we did there is we took the bootstrapping throughput of our architecture of FPT as the baseline, and we sort of did this experiment where we calculated how many CPU or GPU instances you would need to rent to achieve similar throughput. The main conclusion there is that you would need to pay at least 15 times more to achieve the throughput of FPT. To give you one example, let's say you rented these instances here, which have 8 GPUs, you could achieve the same throughput as FPT with one instance of those, which has 8 GPUs, but you would pay a factor 34 more in cost. It turns out that the most efficient you can currently do is to rent a load of CPUs, 135 instances, but still there you pay a factor 15 times more than using FPT. All right, very shortly about future work. We are also working on a large update to the architecture, which will be even faster, also add support for key switching together with a more simple and efficient API. We have one demo that's available on GitHub that was also evaluated as an artifact, and we will work on adding more demos to there. I invite you to have a look already at the demo that's publicly available. It's a small application that you can run currently on AWS. You can use our hardware acceleration and see that it actually works. Thank you.